I organize this mini course. First, we're going to start with a very basic thing. There is the simplicial complexes. Which is the thing that we mostly study on topological data analysis. And in all topological applications, we will see this term appearing over and over during this school. Then the next thing that we're going to talk about, which is required to understand persistent homology, is homology. Need to understand what that is, and then we're gonna and then after covering these two, I'm gonna talk about check complexes, some very important complexes, specific complexes, the Beatrice-Riggs complex, and the alpha complex. After that, I'm going to move to persistent homology. Homology, where I'm going to cover I'm going to cover what a persistent diagram is. What a persistent diagram is, and later, and we're going to show some properties like stability, the stability. Oh, sorry, that's not the way. The stability of persistent homology or persistent diagrams. That's the plan. Yeah. So we're going to finish with persistent homology and show the definition and basic properties and some examples. So if you already know all these topics, it's going to be very boring for you. Okay. So let's start with the first part. So we are going to cover these four things in the 3 sessions that we're going to have today. Right? That's all. So simplicial complexes. Simplicial complexes is something that Jesus already talked about. Simplicial complexes. Simplicial complexes. So basically is what you already know. So simplicial complexes are just the first thing that you need to know about simplicial complexes is what is a simplex. A simplex is just a subset of Rn. We can think about a subset of Rn determined by n vectors, n plus 1 vectors in Rm. Where this set of vectors are in general position. And this notation means is the closure, the convex closure. Or convex call, also somebody called them like that. Some examples, some simple examples is, for example, in R2, you can take any two vectors, not parallel vectors, for example, this vector and this other vector, and then the convex closure will mean the connection between these 2 points. This is VW. This is going to be VW, right? This is what we mean. So, and as you can see, these things are always segments, points. This is, and we call this an n simplex because it's generated by n plus 1 vectors. So, for example, this one here is a 1 simplex. It's generated with 2 vectors, right? So it's always the number of vectors minus 1 is the name of the dimension of the vector. In this case, 1 simplex has 2 vectors. So so in general, they look like this. Like this. So you have a 0 simplex. It's just point Anywhere that you draw it is going to be just point. A one simplex, anywhere you draw it, it doesn't matter what dimensional space you draw this is going to be just segment. A two-dimensional simplex is going to look like a triangle. And a three simplex is going to be a tetrahedron. Yeah. It's going to be generated by the four vertices. It's going to create a tetrahedron. And well, it is hard to draw a four simplex, but it's because you need a space of dimension 4 or 5 to draw it. So at this point, this is a good moment to stop drawing simplexes. And so that's a simplex. And these simplexes are the pieces used to build simplicial complexes. But in order to start talking about how to build a simplicial complex with the simplexes, we need to talk about phases, the phases of a simplex. So it is sigma prime is a phase of sigma if sigma prime is the closure, the convex closure of a subset. So, for example, if you have a triangle, you have the vertices, then you have the closure. You have as faces, you have V0, V1, V2, which are just the vertices, or just this. So the vertices are faces of the triangle. And also you have V0, V1, V0, V2, and V1, V2 are also faces, but these ones are one-dimensional faces. So this is one simplexes. So you talk about these are 6 faces of the simplex. And we denote as with this notation is the union of sigma prime. The sigma prime is a phase, a proper phase of sigma. So that's the boundary. The boundary is the union of all these phases. In the case of a triangle, this is the boundary. So the boundary is defined just in terms of this convex construction, right? So these are just this combinatorial way of defining boundary. Once that you define boundary, then you can define the interior. So probably I can just move this up, right? A little bit racing. Oh, sorry. And yeah, nice. Oh. So then we have the interior of a simplex is just going to be it's going to be the simplex minus the boundary of the simplex. Mm-hmm. Yeah. So in the case of the triangle, it's going to be just this part in the interior. So you don't consider the edges nor the vertices. So this is the interior. So by this definition, a consequence of this definition is that if you have just a vertex, what's the interior of a vertex? The vertex again, which is surprising, right? That the interior of just one vertex is again the vertex, but that's what it is. And so, and this is really important. It's an important property of the vertex. So now we can define the simplicial complex. Simplicial complex. This is just the definition. Simplicial complex. I don't know how. Oh well, I wrote here simplicial complex, but what I'm going to define here is a simplicial structure, a simplicial complex structure. Simplicial complex structure. Well, no, just okay. So if K is a collection of such that. So a simplicial complex is just a collection of simplices. You just take as many as you want, and with the following property: if you have a complex and sigma is a phase. I forgot to mention that this symbol refers to being a phase of a simplex. So this is the way of saying that sigma is a phase of tau. This implies that sigma is also in K. So a simplex is it's a collection of simplexes where all the phases are also belong in the simplex. And two, that if you have two simplexes, that implies that sigma intersection tau is a phase. It's a phase of sigma and tau. Mm-hmm. Which, sigma and tau. Mm-hmm. So this is the basis of being a simplicial complex. So examples of things that are simplicial complexes is just take random triangles and edges and other triangles. This is a simplicial complex, right? But when you draw with something like this, you're thinking that the simplicial complex that you are drawing here is, if you call these vertices B1, B2, you are considering the collection of vertices. You're just considering the collection of vertices. Also, you are considering the edges. And the faces. So when you think of a simplicial complex, you have all these structures. You just the vertices, the edges, and the faces. All of that is all the things that are drawn here. Yeah. Examples that are not simplicial complexes. For example, if you have something like this, it's a collection of two triangles, but the intersection of these two triangles is nothing that looks like a simplex, right? But it can be something like this, or you can also think of something like this. The intersection between this simplex sigma and this other two-dimensional simplex tau, the intersection is just one vertex, which is in this vertex does not belong to it's not a phase of tau. It's not a phase of tau, so that's why it's not a simplicial complex. So, so if K is a simplicial complex, we can think of all these simplices to be on the same dimensional space, and so we can define. If K is a simplicial complex, we can then define we denote as we write K equal is the union of all the elements of K, which is a subset of Rm. Is this the geometric geometric realization? K. This is well, this is what more or less what we think about simplicial complexes. So we have a space of simplices, and then if you think if you take all these simplices as part of our n-dimensional space, you can take the union of all these pieces and you can construct a subspace here. And we think of this like the space with this is the topological space that is referring to this simplicial complex structure. Here, there is a note. This definition doesn't work in general, is because, well, in order to this to be the geometric realization, we need something around the lines that each like locally finite simplicial complex. Okay. Otherwise, if we don't include, well, then the meaning of locally finite simplicial complex, that means that you have a vertex, for example, there are only finitely many simplicial complexes that contains that as a face. For example, we mean there's just 4 edges coming out of this vertex. Because if you allow to have infinite many, things can get really weird. For example, if you have the circle with all the lines coming out of here, this is not a simplicial complex structure on the circle. So this is not a circle. We don't want this. We are not allowing this. Yeah. So, yeah, if you take all the lines coming out of the vertex, each line is a simplex. If you take the union of those, it's a circle. But this circle is not really described by this simplicial structure. Yeah. This is whenever we think about simplicial complexes and we think about lines coming out of the vertex, we think that all those lines are separate. And these ones are very close to each other. This cannot be realized in this way. So that's why we usually think it's just finitely many, so we can have this discrete version, right? But well, for the purpose of this course, we are going to think about the geometric realization just as the union of the simplexes. For example, in this case, it's just the union of these things. It's just the space R2. It's a subspace of R2, and this is the topological space that we are talking about. And one about geometric realizations is that if we have any erasers, well, we say that X is a triangulable space. Probably that's not the way that people usually say it, and maybe it has a triangulation, something like that. It meets a triangulation, or it has a triangulation. But in Spanish, we usually say triangulable. But that's why probably I wrote it like this, huh? Triangulable. But that's also an English word. Triangulable space is a triangulable space if there is a simplicial complex K such that X is equal to the geometric realization of K. So a good example is, for example, you take the circle in the R2. You can think of it like more. Well, this is isomorphic. This is homeomorphic. Yeah, so it is homeomorphic to the geometric realization of a simplicial complex. So if you have a circle, this circle is not a simplicial complex as it is, as is drawn right now. But if you just draw some lines, like for example this, for us, this is the simplicial. This is the triangulation of the circle. Yeah. And so this is the simplicial structure given to the circle, because these two spaces are homeomorphic. These are the same as topological spaces. But these things are not unique. For example, you can have something like this, right? It's also another simplicial complex structure on the same topological space. Well, the simplicial complex structure is kind of rigid, compared to other complex structures like cell discompositions, but they are kind of what was the word that I was using? Rigid. Right. They're kind of rigid. For example, consider T, which is S1 cross S1, which is the torus. Remember, this is this thing. We can try to give a triangulation to this thing, a simplicial complex structure to this thing. And so one way of doing it is, remember, the torus can be seen as a square, identifying these two sides and then identifying these other two sides. This is the torus, right? So if we want to give a simplicial complex structure to this, well, we might think that dividing by the diagonal will give us two triangles, and then we have a simplicial complex structure, which is not okay. Because the intersection between these two, T1 and T2, the intersection between these two is this line, but also this line, and also these two lines. So the intersection between these two faces, this two-dimensional simplex, is not just one face of each other. It's also the entire boundary, right? So that means that they are not. This is not a simplicial. This is not a simplicial complex. Well, then we might try to do something different, like instead of dividing like that, dividing by 2 and cutting like this. Then we have a lot of triangles. But we still have a problem, right? What is the problem? For example, if you take, if we take this triangle and this triangle, what is the intersection between these two triangles? Is the point here, right? But also this point here, which is identified with this other point. So the intersection is 2 points, which is not a face. Each of them is a face, but together are not a single face. Mm-hmm. So that's why this doesn't work either. So not a simplicial complex. So we want to look at it as a simplicial complex. We have to do something more complicated. And this turns out to be the right way of doing it. We need to use 18 triangles. So using 18 triangles, we have a simplicial complex structure. And now each pair of triangles only intersect in just one edge or a point. That's what is happening. So this is the right construction. This is the simplicial complex structure for the torus. So this kind of triangulations?
Yes.
Yeah, it's always possible. Yeah, you can always start with every orientable surface, for example. It can be seen as a 2n agon, a polygon of 2n sides. This is a octagon, right? And so you need to identify this side with this side, this side with this side, and A2 with A2, and B2 with B2. So you do all these identifications and you get this thing.
Thanks.
And so you can start from here and start cutting in pieces and you will get a simplicial complex structure. That's a really good question. I don't know. It is no. Yeah. Did you know it? That was a trick. So why don't you tell them? So do you have it there? No. Okay, but it is. Yeah, it is. It is a known result. It's solved, but yeah. So you can always find a minimal triangulation. Yeah, that you need to get a simplicial complex structure. So as an exercise, you can try to triangulate something that we call the Dunn's hat. Something that we were doing in the hallway some minutes ago. The Dunn's hat is just a triangle with this side identified with this side, identified with the bottom side. So the three edges are identified in just one edge. So as it is not a simplicial complex because you have this thing is this is not a triangle because it has just one edge as a boundary. So what you need is that you have every triangles need to have exactly three boundaries, three edges. So you need to subdivide this in a way that you have enough. If you have triangles, separate triangles, and each triangle intersect with another one in just one edge or a vertex. So something that you might think is that you probably need to subdivide something like this, but that doesn't work. So you need to look for some other options. It doesn't work. Or for example, this one also doesn't work. So you need to look for different options. So just an exercise for you to do in your free time. Did you find it? Well, you can Google it. It just also works. That's all. I think that's all about simplicial complexes. Oh, there is one more thing about simplicial complexes. There's something that you will hear a lot, is that the way that we treat simplicial complexes so far is that basically they are describing a geometric object, and you can just take the geometric closure, the geometric realization just by taking the union of those pieces. But there is a way of defining simplicial complexes that doesn't require you to use pieces that are already embedded in a space. So in this case, we are just using as pieces triangles, a very specific triangles embedded in a space to describe the simplicial complex. But we can do the same thing using something that is called a simplicial structure, something that is called abstract simplicial complex. Complexes. So we can just one of the advantages of having simplicial complexes is that you can describe the structure of the simplicial complex just by looking at the edges, at the vertices. So for example here, you just have a number of vertices: B00, B11, B12, B13, B14, B10, B12, B1. I forgot what order was following. This one, 101, 02, 03. Yeah, like a matrix, exactly. 20, B21, B22, and B23. These at the side are the same as the ones on the other side. So probably that's enough. But for example, here, I'm going to show you in this case, these vertices are all identified to the same point. All of these vertices are the same. And this edge is the same as this one, and this edge is the same as this one. In this case, you cannot use the vertex to refer to the edge. But in this case, you can. For example, here, you can refer to this edge as the vertex that goes from 0, 0 to be 0, 1. This is an edge. And there is only one edge that has those vertices as its ends. So this, if you take any two vertices, there is only one edge that contains those vertices. That's something that doesn't happen here. For example, here, if you take this vertex and this vertex, well, I'm going to use another color because I already have blue in there. So for example, these two vertices, this vertex and this vertex are located here, are identified there, and also I don't see any problem. I don't see any problem. Here. What, this other corner? Okay, this other corner. Okay, yeah, excellent. Thank you. So we have this vertex and this vertex are the same, and this vertex is in between. So if I use, what is the edge AB? Which edge refers to? It can be this one, or it can be this other one. So this symbol doesn't identify a unique edge. That's not, right? So that's why we don't like this kind of triangulations. So that's why we prefer simplicial complex structures, because if I take any two vertices, it refers to only one edge, one specific edge. If I take three vertices, it refers to just one face, one single face. So we can describe the complete simplicial complex structure just by labeling the vertices and saying all the pairs that refer to edges and all the triples that refer to faces, and we can input that into the computer. Yeah. This one also can be put into the computer, where it requires a more complex structure to get it in, right? But it can be also put into the computer. But this is why we prefer this kind of structure. And some inference, and also for some other theoretical reasons. So definition. So we can just refer to this collection of vertices and faces as an abstract simplicial complex. So an abstract simplicial complex is a collection. It's a collection of subsets. Of vertices. Vertices. Such that alpha is an A, and beta subset of alpha implies that beta is an A. So here, a collection of subsets. Well, vertices is just a word that subsets of another set. It can be another set. It doesn't need to be a collection of vertices, but we always think of them like vertices. But so what we have here is just a collection of things. Example, for example, we can think of K as just A, B, and C, A, B, and C, and also the AB, BC, and CA. Something like that. So it's a collection of subsets, and whenever we have, also, I think that we need to add the empty set, just for completion, yeah. So any set and and if we have a set, we have all its subsets. Well, this thing is called an abstract simplicial complex because it's not referring to any specific triangulation and no triangles in any specific space. But we can always realize it geometrically into a simplicial complex, an actual simplicial complex. For example, this one can be realized as a triangle, right? We have here A, B, and C, the edges of a triangle. So once we have a collection of vertices, a set of sets satisfying this condition, we can construct a simplicial complex. And this is a theorem. In fact, it's a theorem. This is a geometric realization theorem. This I'm going to leave it just finite abstract simplicial complex. Abstract simplicial complex of dimension D has a geometric realization in R t plus 2t plus 1. So that means that by just considering abstract simplicial complexes, we are not leaving anyone behind. So we actually have an actual simplicial complex. Has a geometric realization in RD. So there is a space. That admits a simplicial complex structure, and if there is a collection of triangles, and there is a collection of triangle of simplexes that live in R2D plus 1 that realize all the geometry described by this abstract simplicial complex. So that's it for simplicial complexes. Any questions? No? Okay, so now talk about simplicial complexes that appear on point clouds. From data points. By data points, I mean subsets of R M, right? So if we are taking a finite subset of RT, then I'm going to construct a simplicial complex associated with that set. Before talking about this particular case, I'm going to talk about something that is being used in topology for many years, is the nerve. If I have F, a finite covering of a space, of a topological space, X, we can construct the nerve of F. This is a way of constructing a simplicial complex. It's just the subsets of F such that the intersection of these subsets is not zero. So the nerve is an abstract simplicial complex. Okay. So this is a way of defining simplicial complexes. Usually the way that you're going to find them in topological dense analysis and other areas is just they define it in an abstract way. So this in this way of defining it, we can use, for A, we can use any set. It doesn't have to be a set of points. It can be a set of anything. In this case, A is a family of sets. And so the vertices are basically each element of F, and the faces and all the simplexes are constructed as subsets of those. Subsets that have not empty intersection. This is the nerve. So I can give you a drawing of how this nerve thing looks like. With your drawing of it. So it is an abstract way of defining sets. For example, if I have a topological space like this, and I have some how am I doing on time? 15 minutes left. Okay. Okay, so for example, we have here is an open set. Here is another one. And another one here. And we take another two blue, and what else? We have there blue and red. Red is already there. It's purple. Mm-hmm. Another one and purple. So you can barely see anything, right? So at the end of the day, we have to mark a point for every set. In this case, I need to mark a point for the green set. I need to mark another point. Well, 1, 2, 3, 4, 5 points, right? 1, 2, 3, 4, 5 points. And this one is for the brown. And this one for the blue. Where is the blue left? Okay, blue here. And we have another pink here. And a purple. I think it's better for the purple to be here and the brown here. So we are setting 1 point for each set, and if they have non-empty intersection like the green and the pink, we add an edge between those two. If we have, for example, this intersection between the pink and the blue, we have an edge. Between the green and the blue, we have an edge. And between the three, we have an intersection, another empty intersection. So we have to add a face, a two-dimensional simplex. And we have to do all of that for every pair, right? In this case, we have to add this one. I think we have to add this one too. Between the blue and the brown, we don't have to add any. But between the green and this one too, the brown and the blue, no, the brown and the pink, and I think these two and this face, and in between these two as well, and we have something like that, right? And we have an intersection between the green and the purple, and we have all the people intersections. That's what we have. So this from this collection of open coverings, we can construct a simplicial complex, which is called the nerve, the nerve of the covering. So, and this is a very common way of constructing from a data set. We call something that is called this check complex. This check complex, which start with a subset of R, what we call Rm. So and for each A, we take Bx, BIR, which is the ball of radius R with center R, with center A. So on each point A, we create a ball of radius R. Right? So, and then we create this family, this family, which is just the balls of R with A and R, and we take the nerve. So the check complex, the check complex, the check of R is going to be just the nerve of F. inner event. So given this family of balls, we construct the check of the check complex of F. That's what we call the nerve. No? So that's the check complex. And how it looks like is kind of the same like this, but instead you have something like this. You have balls of the same radius, and you have balls of the same radius, and the complex, it just looks like this, right? You just connect the radius and add faces if there is a double or triple intersection, and that's the way that you construct the check complex. But all these balls have radius r. So this complex is one of the main objects of study in persistent homology. So we want to understand the topology of this simplicial complex. Okay, there are other variations, which is the Vietoris Rips, the Vietoris Rips complex. We basically use the same idea, but instead of considering the nerve, it just consider the diameter of sigma is lower than 2r. So all the set of vertices says the diameter of that set is at most 2r. So there is so this is also an abstract simplicial complex, and that gives you a simplicial complex structure. But well, the main difference between these two can be drawn like this. For example, you have an equilateral triangle, and you have circles of radius just a little bit bigger than 1/2, like a triangle, something like this. Just a little bit longer, yeah, it was more than a little bit. Okay, let's try something smaller, something like this. So in this case, the diameter of the 3 points, the diameter, if this is the diameter is 2r, then we have the 3 points, the 3 points, the distance between the 3 points is, so the Vietoris Rips in this case is going to be just the 3 edges, the 3 points, and the face. But if you just look at the check complex, the check complex is going to be just the three edges, but not the two faces in the middle, because you don't have the triple intersection of the 3 balls, right? So you have the intersection between this ball and this ball, this ball and this ball, this one and this one, but you don't have the triple intersection, the 3 balls. So that means that you won't have a three-dimensional face going here, just the triangle. So this is a small difference between Vietoris Rips complex and the check. But turns out that people likes more the Vietoris Rips because it is faster to compute. So if you want to understand the data, probably the Vietoris Rips is going to tell you basically the same thing, but it turns out that they capture kind of a different information of the set. One of the things about this check complex is that captures a lot more interesting information. You know, they capture all the information of a lot of good information. This is what is called the nerve theorem. This is a theorem from algebraic topology, the nerve theorem. It's the nerve theorem. If F is a family of contractible contractible sets with contractible intersections. There is a word that some of you might not know. Then X equal the union of these sets and the nerve of the family have the same homotopy type. So this means that when you have contractible sets, well, if you don't know what contractible is, just you can think of them like things that you can compact into a point, like you just squish it down to a point. So you can squish down to a point a ball. You can just squish it down to a point. It can be squished down to a point. But for example, an annulus is something that you cannot squish down to a point. Right? You kind of destroy the structure. So you can squish it down to, when you squish down, you have to squish down to something inside of it. So you cannot squish down the annulus to a point inside of it, right? Without breaking apart the loop. So that's why this is not contractible, and this is contractible. You can think of that as contractible. So if you have all the open sets that cover your space are contractible, and all the intersection between those are contractible, then the nerve and the space, total space that is covering by these open sets have the same homotopy type. Homotopy type is something really hard to understand when you start learning algebraic topology, but it is one of the key concepts in algebraic topology, because at the end we're going to study homology. We're going to study homology, and homology is something that is invariant under homotopy type. If a space has the same, if two spaces have the same homotopy type, if X and Y are homotopy equivalent, then the homology of these spaces is going to be the same. That's why homology is invariant under homotopy types. So when you talk about what changed between getting rid of the space and changing to the nerve, homotopically it did not change anything. You got the same homotopy type. Something that does not happen with the Beatrice-Rives complex. With the Beatrice-Rives complex, you might lose the homotopy type. Mm-hmm. So, for example, if you're talking about points in a circle, you're talking of balls that looks like this. So the homotopy type of this family of circles is the same that homotopy type of the nerve. The nerve of X of F is going to be they are going to be homotopically equivalent. You can squeeze down the nerve, the circles to the nerve. That's something that this theorem is telling you. But unfortunately, that doesn't happen with the Beatrice-Rives complex. You don't have this preservation of the homotopy type of the space, which is kind of sad. But at least you have something. You have something like they are kind of close. This is an observation that the check complex, is contained on the Beatrice-Rives complex of the same radius, and also contained in the check complex of the square root of 2 times r. So the Beatrice-Rives complex is between two check complexes the one with radius r and the one with radius square root of 2r. So somehow the virtual risk complex is moving closely. Well, is moving interlaced or in between check complexes. And so somehow it captures some of the information. And so that is something that can be reflected later in the way that we compute homology. It is not the same, but it's going to be close enough to the homology of this check complex. So this loses some part of the homology. And time's over. The next session, we're going to see each other in an hour. So we will continue with another complex in the next session.
Okay, let's thank Jesus.
In a moment.
Are there any questions?
So as you say,
it is somebody's.
Okay. Yeah, thank you. You say that the Vietor-Rips complex is easy to compute, right? Using you only need to know the distance between any 2 points, right?
Yeah, I forgot to mention that, but yeah.
Is there any algorithm to compute the check complex? I mean, it could be complex, but at least algorithmically.
Yeah, you just they compute something that is called the smallest ball. Yeah, so that you take any set of points and you can compute the ball, the smallest radius of the radius of the smallest ball that contain those points, and you try to compute that, and that will kind of get you close to the computation of the check complex. Mm-hmm. Well, that's the only algorithm that I have seen. Yeah, but it is kind of, yeah.
Oh, there is.
But that's computers through this check complex.
General TDA in the one of them is to compute echo.
Okay.
They found the station there to avoid the station.
Oh,
The third question is
there is there are algorithms. Yeah, but I'm not very familiar with algorithms. Sorry.
I have a question or maybe a comment about the relationship between the check and the Vietor-Rips complexes. So there is a version of the NERF lemma and that says that, so suppose the intersections are not contractible, but they look like a point up to a certain range.
Oh,
they are homotopy equivalent up to a certain range. And then if you relax the hypothesis in that way, I believe there is a conclusion that then the nerve has the same homotopy up to certain range of the original space.
After certain dimensions.
No, in the first dimensions.
The first n dimensions. Okay.
So I was wondering if there is some kind of relation similar to the check and the complex and the Vietor-Rips complex of that sort.
No, I don't. This is my first time hearing about this relaxation of the nerve theorem, but I think that the actual what is going to happen is that you will have a relation between the persistent homology of this thing and the persistent homology of this thing. There is going to be you have a bound, an upper bound in between the distance between these two. Probably that will preserve with the dimension in that case. Well, if you have in the range of dimension, according to that.
So I had a curiosity. It was mentioned that with the Beatrice-Rips complex, we do not recover the homotopy type of this space. Could we see an example of what we mean by that?
Yeah, well, the example basically is the one that I just drew here. And these examples happens a lot. So we have the three balls like not intersect. Every two intersection happens, every pair of intersections happen, but not a triple intersection. So the homotopy type of this thing is basically the same of an annulus. Because you have here this ball, and this ball, and you have this hole in the middle. So this hole does not disappear with homotopy type. When you preserve the homotopy type, this hole will still be there, needs to be still there. So if you use the Beatrice-Rips complex, it's gonna cap it off that hole, and that will change the homotopy type of the space. So this is so the check complex. The check complex is gonna give you this, which still have a hole because there is no triangle in here in the middle. But if you take the Beatrice-Rips, it's gonna give you a triangle with a face in the middle, with a two-dimensional face in the middle. And this is the homotopy type of a point. This is basically contractible, and this is not. So that the homotopy type change when you use Beatrice-Rips, and this is the homotopy type is different. This is the same, but this is not the same. This is an example.
Thanks. I understand. We were comparing the homotopy types of the Czech and Beatrice-Rips.
Yes, yeah.
Not the, okay.
Yeah, well, in fact, we are comparing the homotopy type of Czech Beatrice-Rips with the union of the three balls. With the union of the three balls has the same homotopy type of the Czech, but the union of three balls doesn't have the homotopy type of the Beatrice-Rips.
Till set time.
Thank you.
After certain radius, yeah.
Because if you grow the radius, eventually you will go in the triangle.
Yeah. After when you raise the radius to square root of 2, the balls are gonna cover the hole. But it can happen that another hole appears somewhere else, and then you are not sure if you are now in the same homotopy type. But you know that you're between the homotopy type somehow.
Any other questions? Well, if there are no more questions, let's thank Jesus again.